All right, mathletes, here's 2.5 piecewise functions. So with piecewise functions, we're going to have multiple relationships being used to define a single function. These relationships are unique to certain intervals. For instance, this function f of x, you'll use the relationship x plus 1 if your x's are greater than 2. Well, if your x's are less than or equal to 2, then you'll use the relationship negative 2x plus 5. So what this would look like graphically, I can go ahead and use Desmos here, and I can see that for my first one, x plus 1, I have a graph like this. If I think about it, I want my graph to be x greater than 2. So it's in theory like taking a sketch and cutting out this graph. So I only am going to use this graph from x equals 2 and greater than that, and not quite greater than that. So as I put this into my function, I take that snippet and I'm going to only use it from x values being greater than 2, non-inclusive to 2. So I want to make sure I leave an open circle at 2 to show that it's not defined by that function at 2, but here this function will define it at 2 in values less than that. So I'm going to go ahead and use Desmos to help us out here, and I'm just going to graph that function, negative 2x plus minus 2, and I'm going to take a snippet, and I'm going to snip it from negative 2, or from 2, and everything negative of that is going to be defined now of this function in blue, negative 2x plus 5. Okay, so now that I have that graph, I overlay this graph for all values less than or equal to 2. So these are going to go off like this. This is defined at 2 because it's equal to. So I'm going to have a closed dot, and I know that this still passes our vertical line test because the dot from the previous one is open. It's not defined there, but at 2 it is. So I would use the blue one to find the answer for 2. Okay, so that's my function. Notice it passes our vertical line test, but I also often refer to piecewise function as our kind of cut and paste functions. They're going to be cut and paste defined by these conditions on the right side. So often algebraically, when you're trying to solve for f of x, you need to work from the right to the left in order to evaluate something. So the domain of this function, I can see, well, I'm going to go, the blue function is going to go left and up forever. The red function is going to go right on forever. So our domain is going to be for all real x's. Notice both my relationships are polynomials. Those are going to be defined all over our domain. Okay, our range is going to be a little different here. So I notice that my ranges, I can have values. My lowest value I can ever have here is when y is equal to 1, and it's going to be defined at every other place above that. So my range is for all real y's such that y is greater than or equal to, it can be equal to 1 there. So where y is greater than or equal to 1. So if I want to evaluate this function at f of 0 and f of 3, this is my x value. So again, like I said before, read this from the right. So I need to decide, am I going to put it into my red equation or my blue equation? Well, 0 is less than or equal to 2. That means I want to use the second equation to evaluate the function. So I do f at 0 is equal to negative 2 times 0 plus 5. And I'm going to see that that is equal to 5. Right? If I look at 0, I can see that that point lives right there at 5. Well, f at 3. Well, 3 is greater than 2. So reading this from right to left, it meets this condition. So I want to use this function. So it's going to be 3 plus 1 is equal to 4. So I can see at f of 3, I have a value of a function at 4. Okay, let's go ahead and look at another example here. All right, in this piecewise example here, we have 3 different relationships defined over 3 different intervals. So 2x plus 1 is going to be for all x values less than or equal to negative 1. So if I go to Desmos, I go ahead and turn on 2x plus 1. I know that our function is going to be defined from negative 1 and to the left of that. So I'm going to go ahead and snip all my values of my function from negative 1 and on, so that's going to be to the left for this decreasing function, and that's going to be my graph for the next piece. So I can move this into place and see that this is going to be my function from negative 1 and to the left of that. It is inclusive at negative 1, so I'm going to have a closed circle and arrow showing that it goes on forever. The next piece is going to be a constant value of 3. So my y is going to be equal to 3 from negative 1 to 1. So again, I'm going to pull up Desmos, constant function 3 from negative 1 to 1. So I'm going to snip that interval, and from negative 1 to positive 1, that function is going to be defined there at those points. So as I paste this in here, this function here in blue is going to be defined there. Notice at negative 1, it's non-inclusive, so that's going to be an open circle. That there to throw you off. And then at 1, it can be defined there at that function, so it's a closed circle on this right side. So the last piece is going to be x squared plus 1. So I can go ahead and graph that parabola here. I get x squared plus 1, and that's going to be for all of our values. As I snip it, it's going to be from 1 and off forever to the right. So as I paste this here, okay, and I can see, again, it's non-inclusive, so I have an open circle here. Notice this still is passing my vertical line test. That at no point is anything defined twice at any given point. So let's go ahead and talk about domain and range. So it looks like our domain for this function, I have no gaps as I think about going from left to right, that the function is defined here in the red. As we get into this area, I see that it's always defined here, and then it's defined to the right, so the domain is for all real x's. No issues. None of these 3 functions independently have radicals or are rational dividing by something. So we have for all real numbers for our function f of x. And let's think about our range. So now with our range, I'm going to think about this as I want to know what possible y values there are. Well, going from the bottom, it's going to be fine, but notice I have kind of a dead zone here. No functions have an output in that range. Then the green function here takes over, and I get all those possible values above, because I know that this function is going on forever that way. And so I have this kind of dead zone. It looks like from 2 to negative 1, that my function will never be in that range. So as I write this, it's going to be for all real x's. So I kind of have a split interval here. So I'm going from negative infinity up until this point. So that's going to be at -1. It can be included there. So negative infinity to -1. And it's going to go from, so at this value, my y value is 2. So I'm going to go from 2 to infinity. So such that those conditions are made. And because it is range, it shouldn't be x, it should be y for all real y's. Okay, evaluating our function, f of 0 and f of 3. So again, I read these from right to left. When x is 0 is going to satisfy this condition. So f at 0 is going to be equal to 3. That's nice. You can see on my graph at 0, my value is 3. So if I evaluate that at f of 3, okay, 3 is going to satisfy this condition that it's greater than 1. So I'm going to use this function. So 3 squared plus 1 is equal to 10. And again, I can come over here to 3 and see that I have a value of 10 on my graph there as well. For our last example here, what we have to be able to do is go in the opposite direction. So we want to be able to go from a graph and define a piecewise function. So I'm going to break this into 3 sections here. So I see I have this cut and paste piece in the red. I'm going to have this piece here in the green, and I'm going to have this third piece here in the red. Notice the open circles and the closed circles here. So let's just start from left to right. So f of x is equal to, and I need 3 of them. Well, this graph in the red, it's an equation of a line. I can see that it includes the point -3, 0 here, and it includes the point up here at, this is 4, this is -5, so -5, 4. I can calculate the slope of that is going to be 4 minus 0 over -5 plus 3. So I'm going to get 4 over -2, which is equal to 2, which should make sense. I go down 2 over 1 here, and then down 2 over 1 there for the slope. Okay, it includes the point -3, 0. So point slope form, I can do y minus 0 is equal to -2 times x plus 3. Change the sign there. And I get the equation of my line, which is y equals -2x minus 6. If I imagine this graph had come down here, and it would have a y-intercept at -6, so that should make sense. So this is -2x minus 6. Well, what interval did I get that from? So I'm going to go ahead and kind of move some of this out of the way. So the interval that I got this from is from that point -3, 0. So I cut and paste right there. So from here over, so I want x's, which are less than or equal to -3. I can even, because they meet at the same point here, I can either define -3 being 0 here, or for my green function, I just don't want to do it for both, so I don't want any overlap there. Okay, so if I'm including -3 here for my green function, or in my red function for my green function, my -3 and to the right is going to be non-inclusive, so no equal sign there. So what's the equation of this line in the green? Well, I have the point -3, 0, and I have the point 0, 3. That's a slope of up +1. and I can see my y-intercept's 3, so that's just going to be y equals 1x plus 3 is that graph. And so this is what happens if x was less than negative 3. If x is in between negative 3, and again, where am I going to cut this line? Well, I need to cut it right here. So that's when x is 0. So from negative 3 to 0, the green function is defined. So x is greater than negative 3, but it's got to be less than 0. At 0, notice it is a colored in dot here. So I need to define that function, and it's inclusive there if x was 0. My last function's in the blue. It's a constant function at y equals 2. So it's just going to be 2 here. And that's if, again, I have an open circle here. So that's non-inclusive, but it's going to be when x is greater than 0. Okay? So domain and range, and calculate some values. We should see that the domain of this function is for all real x's. I don't have any holes as I move from left to right. And my y, and now for my range. So range, notice the red function is going to be increasing forever as we go left, but we cut it off the decreasing. So nothing's ever going to drop below this axis. So our range is for all real y's such that y is greater than or equal to 0. Yes, at this value, we can be equal to 0, but we're never going to have any values less than that. Okay, so f at 0. So f at 0, again, left to right. 0 satisfies this condition here, so I need to put it into that equation. That's going to be 0 plus 3 is equal to 3. Sure enough, when I go to 3, I see that point there. So f at 3, well, that meets this condition. It's greater than 0, so it's just equal to 2. Don't have to do any arithmetic. Any value, any x value, give me greater than 0 here is going to be 2. So f of 1,523 is equal to, you guessed it, 2 as well. All right, that concludes our notes for tonight on piecewise functions. Make sure you highlight any questions and bring them to class tomorrow.